Take a look at water in its liquid or solid state. It flows easily at room temperature and boils away with relatively little heat. Compare that to diamond. It is so rigid and unyielding that we use it to coat the teeth of heavy-duty industrial drill bits to tear through solid rock. Then there is copper. It can be pulled into hundreds of miles of thin wire without snapping, while conducting massive amounts of electricity. If we zoom in past the macroscopic surface of these objects, down to the subatomic scale, we find that these completely different behaviors aren't random. A material's melting point, its physical rigidity, and its ability to conduct electricity are direct results of exactly two variables: how its atoms bond to one another, and whether its electrons are locked in place or free to move. Nearly all physical properties can be explained by three distinct architectural frameworks: simple molecular, giant covalent, and giant metallic. To predict how a substance will behave in the real world, we have to approach chemical bonds as microscopic structural engineering. We have to map the internal geometry. We begin our investigation with simple molecules. These are discrete, finite units made up of a specific, limited number of atoms. These atoms are held together by covalent bonds, sharing pairs of electrons to achieve a stable, full outer shell, a noble gas configuration. Look at this diagram of methane, CH4. The 2D dot and cross model shows exactly how electrons are shared, translating into a discrete 3D shape. The covalent connections locking the carbon and hydrogen atoms together are called intramolecular bonds. These are immensely strong forces, operating within the molecule itself. But when we pull back to look at multiple methane molecules floating near each other, we see a different force at play. The separate molecules interact via weak intramolecular forces. When you heat a simple molecular substance to melt or boil it, you are not applying enough thermal energy to break those strong, white intramolecular bonds. You are only overcoming the faint, weak forces between the separate molecules. Because those outer intermolecular forces require very little energy to sever, simple molecular compounds inherently possess low melting and boiling points. This localized structure also dictates how they respond to electricity. Every single outer electron is strictly occupied in a covalent bond. There are no free-moving charged particles available to carry a current, meaning these substances cannot conduct electricity. Simple molecules act as isolated structural islands. Their macroscopic weakness and their insulative properties come entirely from the empty gaps between them. If we remove those empty gaps and allow covalent bonds to extend continuously and infinitely in all directions, we get a giant covalent structure. The element carbon provides the clearest case study for exactly how 3D geometry controls physical reality. In this model of diamond, notice how every carbon atom forms 4 strong covalent bonds with its neighbors. This pattern repeats endlessly to form a 3D tetrahedral lattice. Because the strong intramolecular forces extend continuously in 3 dimensions, there are no weak points. The interlocking geometry creates a material of extreme structural rigidity and hardness. And because all 4 valence electrons of every carbon atom are locked tightly into those localized bonds, diamond is a perfect electrical insulator. Yet carbon can also exist as graphite. In graphite, each carbon atom only forms 3 covalent bonds instead of 4. This shift in geometry generates a flat, 2-dimensional hexagonal sheet, which stacks in parallel layers. The unbonded 4th electron from every carbon atom detaches from its parent nucleus. It pools into a delocalized layer sandwiched directly between the stacked sheets. Mechanically, the forces holding these layers together are incredibly weak. Under light pressure, the sheets shear and slide past one another. This allows graphite to act as a highly effective dry lubricant. Electrically, those unbonded electrons are highly mobile. When a voltage is applied, they flow rapidly between the gaps, making graphite an excellent conductor despite being a nonmetal. This represents the carbon paradox. Material hardness relies on continuous 3D bonding, while electrical conductivity requires mobile, freely delocalized particles. These architectural rules apply just as rigorously to chemical compounds as they do to pure elements. Consider silicon oxide, commonly written as SiO2, the primary component of sand and solid quartz. If we look at its atomic arrangement, Each silicon atom bonds to 4 oxygen atoms, and each oxygen atom bonds to 2 silicon atoms. It creates a continuous, interlocking tetrahedral network. By mirroring the dense, repeating geometry of diamond, silicon dioxide exhibits the exact same physical traits: a massive melting point and extreme hardness. Structural geometry supersedes elemental composition. If a compound is arranged in a continuous 3D covalent lattice, it will possess immense rigid strength. This brings us to the third fundamental architecture, the metallic bond. Metals form a highly regular, three-dimensional lattice, but unlike a covalent network, this grid is made entirely of positively charged metal cations. In a metal, the valence electrons detach completely from the individual atoms. They form a dynamic sea of delocalized negative charge that entirely surrounds the rigid positive cores. The strong electrostatic attraction between the positive lattice and the negative electron sea holds the entire structure tightly together, giving metals their typically high melting points. But why don't metals shatter under physical pressure, the way giant covalent structures do? Why are they malleable and ductile? When physical force is applied to a metal, layers of positive ions are pushed past each other without the lattice fracturing. The fluid electron sea instantly shifts and adapts around the moving ions, maintaining the electrostatic attraction. This unique fluidity also dictates their electrical behavior. Because delocalized electrons are completely free-flowing, they effortlessly carry massive electrical currents through the metal. While graphite limits delocalized electrons strictly to 2D planar gaps, a metal lattice allows them to move unimpeded in all 3 dimensions. Metals represent an ultimate hybrid architecture. The electron sea acts as continuous electrostatic glue for high strength, while its inherent fluidity provides unmatched physical adaptability. To predict how any substance will physically behave, you only need to determine its lattice continuity and its electron mobility. We can see this engineering logic clearly when comparing our 3 structural models side by side. Locked electrons isolated inside discrete units result in low boiling points and thermal insulators. Continuous, locked covalent networks result in high structural strength, high melting points, and electrical insulators. And delocalized electrons, moving freely around a fixed lattice, result in high physical malleability and high electrical conductivity. The macroscopic reality we interact with every day is entirely programmed by these microscopic rules of electrostatic engineering. Level up your study game today. Go to www.studybuddy.tech to take our completely free diagnostic test.